Hi, welcome back to NPA teaching. In the last video, we had higher order derivatives with the function of one variable. We will also have the higher order derivatives of a function of more than one variable. However, this time we will have more options since we have more than one variable. Consider the case of a function of a two variable x and y. Since both of the first order partial derivatives are also the function of x and y, we could in turn differentiate each with respect to x and y. This means that for the case of a function of two variable, there will be a total of four possible second order derivatives. That is, to take the derivative, we must take a partial derivative with respect to x and y, and then there are four ways to do it. That is, x then x, x then y then x, and y then y. Given a function z is equal to function of x and y, the second order direct partial derivative signifies that the function has been differentiated partially with respect to one of the independent variable twice, while other independent variable has been held constant. For example, here the direct partial derivatives are f of xx, which measure the rate of change of first order partial derivative f of x with respect to x, while y is held constant. So in this case, we can denote the f of xx by using these notations, and it is the derivative of a function z taken twice with respect to x. Similarly, the another direct partial derivative is f of yy, which measure the rate of change of first order partial derivative fy, again with respect to y, while keeping x variable is constant. So by using these notations, we can denote the f of yy, which means that the derivative of function z taken twice with respect to y. As we have two direct partial derivatives in the form of f of xx and f of yy, we have two cross or mixed partial derivatives which are f of xy and f of yx, which indicates that the first primitive function has been partially differentiated with respect to one independent variable, and then that partial derivative has been turned partially differentiated with respect to other independent variable. The cross partial derivative f of xy measure the rate of change of first order partial derivative f of x with respect to other independent variable y. These are the various notations used to explain the cross partial derivative f of xy. That is the derivative of a function z with respect to x and then with respect to y. Similarly, the cross partial derivative f of yx, which measure the rate of change of first order partial derivative f of y with respect to other independent variable, that is x. So by using these notations, we can also explain the f of yx, that is the derivative of a function z with respect to y and then with respect to x. These are the various notations used to explain four possible second order partial derivatives. That is, two second order direct partial derivatives in the form of f of x and x, f of y and y, and two cross or mixed partial derivatives in the form of f of xy and f of yx. See, here we have a numerical example, that is function z is equal to 7x cube plus 9xy plus 2y raised to the power 5. That means it is a multivariable function where the function z is a function of two variables, that is x and y. Now we are going to differentiate the given function z with respect to x and with respect to y partially. That is, the given function z with respect to x while keeping the y is constant, then it will become the derivative of 7x cube, which is equal to 21x square, plus then the derivative of 9xy with respect to x, it will become 9y. Thus the first order partial derivative with respect to x, that is f of x, is equal to 21x square plus 9y. Similarly, we are going to differentiate the given function z with respect to y. Then we are taking the differentiation of a given function with respect to y while keeping the variable x is remain constant. Then f of y, which is equal to the derivative of 9xy with respect to y, then it will become 9x plus the derivative of 2y raised to the power 5, which is equal to 10y raised to the power 4. Once we received the first order partial derivative with respect to x and with respect to y, then we can go for higher order partial derivatives. For example, second order partial derivative. So in this case, first we are considering the second order direct partial derivative, that is f of xx. That means we are going to differentiate the fx again with respect to x. Then it will become, that is the derivative of 21x square, that will become 42x. Similarly, we are going to differentiate the f of y with respect to y, that is f of yy, which is equal to, we are going to differentiate the y variable, then the derivative of 10y raised to the power, which is equal to 40y cube. Similarly, we can also calculate the second order cross partial derivative, that is f of xy and f of yx. For example, if it is f of xy, then we are again going to differentiate f of x with respect to the second independent variable, that is y. So in this case, the f of x is equal to 21x square plus 9y. Then if you are again going to differentiate this function with respect to y, then it will become 9. In the same way, we are considering the second cross partial derivative, that is f of yx. That means we are going to differentiate the first order partial derivative, that is f of y, again with respect to x. Then the f of y is already calculated, that is 9x plus 10y raised to the power 4. Then this function is again differentiating with respect to x. Then it is the derivative of 9x, which is equal to 9. Consider another example of a given function, that is z is equal to 3x square y cube. And now we want to find the first order, second order partial derivatives of a given function z is equal to 3x square y cube. So in this case, the function we are going to differentiate with respect to x, that is f of x, which is equal to 6xy cube. And similarly, if you are differentiating the given function with respect to y, that is f of y, which is equal to 3 into 3 square y raised to the power 3 minus 1, that is 9x square y square. Once we are calculated the first order partial derivative, then we can go for higher order or second order partial derivative, that is the second order direct partial derivative, that is f of xx. That means we are again going to differentiate f of x with respect to x, then it will become 6y cube. And similarly, the direct cross partial derivative, that is f of yy, which is equal to, we are going to differentiate function f of y with respect to y again. Then it will become 18x square y. Similarly, if we take the cross partial derivative f of xy, that means we are going to differentiate the function f of x with respect to y. Then f of x is, which is already calculated, that is 6xy cube. Then we are going to differentiate it again with respect to y. Then it will become 18xy square. And similarly, the second cross partial derivative, that is f of yx, which is equal to, we are going to differentiate the f of y with respect to x, which is equal to 18xy square. You might have been noticed that while differentiating second order cross partial derivative f of xy and f of yx, that both are giving an equal function or value. Then as per Young's theorem, if both cross partial derivatives are continuous, then the corresponding cross partial derivatives are equal. This is known as Young's theorem. That is, the derivative with respect to x argument of derivative with respect to y argument is the same as the derivative with respect to y argument of derivative with respect to x. This result is named after William Henry Young's, which is popularly known as Young's theorem. That is, f of xy is equal to f of yx. I hope you are clear about how to find the higher order partial derivatives. In the next video, we will discuss the application of higher order partial derivative, that is optimization of multivariable function with suitable economic examples. Have a nice day and see you in the next video. Thank you.